Okay, we've got to do a Kruskal-Wallis test. We've got 4 independent samples this time. We need to test whether there's evidence of any difference between their average scores. So step 1, hypotheses. We need an H0 and an H1. H0, as ever for Kruskal-Wallis, is that the samples come from identical populations. So H1 has got to contradict that. So this is at least 2 of the populations are different. And we can put that in the context of the problem. Not all the children score equally well. It's Kruskal-Wallis, so this is just a difference from H0. There is no one-tailed or two-tailed decision for us to make, because Kruskal-Wallis can't tell us the direction of any difference. Okay, step 2, we've got to calculate the test statistic. First thing we've got to do is just rank all of these scores. So the lowest rank will be 1 for this one, and then 2. So I'll go through and put all the ranks on. So I've got up to rank 21 here, and the final 3, rank 22 is this 1700, and then 23 and 24 are here. So next step of Kruskal-Wallis, remember that the formula that you need is on page 14 of your formula book. So here's our method. So we need a value of n, that's the total number of observations across all of the samples, and then I need the total of the ranks for each sample and the size of each sample. So those are the ingredients I need to set up for my test statistic. So n is the total number of scores in the table, so there are 4 lots of 6, that's 24, 6 4s are 24. Okay, all the little n's, all of the sample sizes are 6. Okay, and I've got to total the ranks for each sample as well. So for the first one, 5 plus 7.5 plus 10 plus 14 plus 18 plus 21. I can plug that into my calculator. I'm going to get 75.5 for my first t. And then t for this one is going to be the total of those numbers. It turns out to be 99. And again, n is 6 for this one. And for this one, I get a t of 93. And n is 6 again, and these ones add up to just in this case 32.5, and n is 6. So I now have to apply the formula. So the formula was h is 12 over n brackets n plus 1 times the sum of t I squared over ni, and then minus 3 lots of n plus 1. So I'm going to focus on this bit first. So I'm going to do each t value squared divided by the n. So I'm going to get 75.5 squared over 6 plus 99 squared over 6 plus 93 squared over 6 plus 32.5 squared over 6. So all the n's are 6 this time, they don't have to be. And when I add those together, I get, oops, I better put this right first. This is 32.5, not 3.25. So when I put that into my calculator, it tells me the answer is 4201.08. 4201.08. So I've just done this part of the calculation. So now I need to do that. I need to do the 12 times n plus 1. Well, n was 24, so this is 24 times 25. And I need to multiply by the 4201.08, and I need to take away 3 times 25. Okay, so on the calculator, I can do 12 over 24 times 25 times my previous answer, minus 3 times, this should be 3 times 25, I don't know where that 27 came from, minus 3 times 25 is 75, so press equals, and I get this number here. I get my test statistic is 9.0217. Okay, so I've got my test statistic, that's step 2. Step 3 is my critical value. Well, I'm going to use a chi-squared critical value. So for chi-squared, I need a couple of things. I need the degrees of freedom, okay, and I need my p-value. So my degrees of freedom, well, with Kruskal-Wallis, we just have to count how many groups there are. So it's 4, not the 24 observations, the 4 groups, and take away 1. So my degrees of freedom is 3. And my p-value comes from the confidence level. So I've got a 5%, which would be a probability of 0.05. But with chi-squared, we always use the high-end probability, so in this case, 0.95. So I go to my chi-squared table. Here it is on page 27 of the formula book. So my p was 0.95, my degrees of freedom was 3, so my critical value is this 7.815. So I have my critical value here, I have my test statistic here, and so I'm ready to do my comparison. So my 9.0217 is up against the critical value of 7.815, and of course it's greater. And because with chi-squared probabilities we're always looking at the high-end values, that means that this has succeeded in being significant. So this is significant at the 5% level, and therefore, because it's significant, we're going to reject our null hypothesis. Okay, and now I need to just finish off by interpreting that in context. So, because we're rejecting H0, we say there is evidence. Okay, and the evidence is that, I've got to put this in context, so yes, it's true that it means that the data don't seem to have come from identical populations, but that suggests that there is a difference in the average scores of the children on the games, so that's what I'm going to write. Okay, so average scores not all the same. Some of them might be, but we don't think they all are. And then it asks us to account for that. Now, this isn't given to us by the test statistic, but we have to go back to the original data and say which of the children does seem to be worse than the others. Because it does seem to be, we've got two with quite high sums of ranks, okay, and high ranks go with high scores. So we've got two children quite good. This one isn't far behind, but poor old Sam here has got a lot of the lowest ranks. So it seems that the reason why we've got a significant result is because Sam is not scoring as well as the others. So Sam is the worst. So which child, if any, performs worst? Sam, because he has many of the lowest ranking scores. That's what's caused the test statistic to be significant. And I'm done.